The last time we met, we were exploring digital modulation methods, specifically the QAM methods. We had walked our way through 16, 64, 4096, 32,768, and we had asked ourselves, is there a limit to the number of unique levels that could be used? And it turns out there is, because of noise. Today, we're going to briefly explore that noise, but more importantly, we're going to introduce one of the most fundamental equations for this entire class, known as the Shannon-Hartley limit. The argument goes something like this. Suppose we have a 16 QAM system. This is important to us because the channel capacity in bits per second is equal to the baud rate by log base 2 of the number of symbols. In this particular example with 16 QAM, there are 16 unique symbols. So at any particular time, this vector will point to one of the dots. It will stay in that position for the time defined by the baud rate. Because there are 16 unique symbols, the channel capacity is 4 times the baud rate. Because log base 2 of 16 is equal to 4. In our previous discussion, we implied that the channel capacity could be increased by adding additional points. In an ideal world, this would work. But we don't live in the ideal world. We live in a world with noise. We live in a world where this vector, when it's transmitted and finally received, doesn't land where we'd expect it to. For example, what does this vector here represent? I tell you, nothing good is going to come from this because that vector is equidistant from each of the assigned points. Chances are very good that this is going to result in a bit error. That noise can cause this vector to change in phase. It can also cause the vector to change in amplitude. In fact, if we were to turn on a persistent display, we would see that as the vector lands on this constellation, there's a cloud of different places that it falls. As drawn, you might consider this to be a low noise environment. However, as the noise increases, the uncertainty of that vector also increases. Now the noise is moderately high, and we might reach a point where the noise is very high. Anyway, I think you see the problem. For example, if the vector lands in this position here, it could be associated with this symbol, or it could be associated with that symbol. If the receiver can't tell where the vector lands, there will be bit errors. Consequently, there is a relationship between the number of levels and the noise in the environment. In fact, for this particular application, instead of using 16 QAM, maybe we would have been better off using 4. With the same amount of noise, the receiver would have no problems determining where the vector is located. So there wouldn't be any bit errors. This tension between the desire to add more levels, but recognizing limitations of noise, brings us to two equations that are fundamental to our understanding of digital radio. The first one is known as Hartley's Law. It tells us that the channel capacity is equal to 2 times the bandwidth by the log base 2 of n, where n is the number of levels. we're going to make a big caveat here. This is only applicable to the ideal world. It says absolutely nothing about noise. As an example, let's assume 16 QAM and 3 kilohertz bandwidth. The channel capacity would be 2 times 3000 by log base 2 of 16. That channel capacity is 24,000 bits per second, which is fine, but this says nothing about the signal-to-noise ratio. To account for that noise, we have another equation known as the Shannon-Hartley limit. The equation states that the channel capacity is equal to the bandwidth by the log to the base 2 of 1 plus the signal-to-noise ratio, where C is channel capacity, B is the bandwidth, and SNR is the absolute signal-to-noise ratio. Absolute here means the non-dB signal-to-noise ratio. You could think of this as a real-world limit that does indeed account for the noise. Continuing on with our previous example, we can now use the Shannon-Hartley limit to determine what the required signal-to-noise ratio is. So that's 24,000 bits per second. We have a bandwidth of 3000 log base 2 of 1 plus the required signal-to-noise ratio. 8 is equal to log base 2 of 1 plus the signal-to-noise. To break this piece out of jail, we would say that 2 raised to the 8th is equal to 2 log base 2 of 1 plus the signal-to-noise ratio. That's 256 is equal to 1 plus the signal-to-noise ratio, which means the signal-to-noise ratio is equal to 255. Or, if you prefer that in dB form, our receiver would require a 24 dB SNR. Something you might find useful occurs when we take Hartley's Law and the Shannon-Hartley limit and plot them on the same graph. This graphic was developed assuming a channel capacity of 1 Hertz. Of course, you could have set this to anything you like, but for simplicity, we set it to 1. The first thing to notice on this chart is the Shannon-Hartley limit. That's this line right here. It is an absolute limit. It's the best we can do given the specified signal-to-noise ratio. For example, if the receiver has a signal-to-noise ratio of about 70, the Shannon limit tells us that we can send no more than 6 bits per second. Capacity in bits per second is B log base 2 of 1 plus the signal-to-noise ratio. Here we see that channel capacity and bandwidth are directly proportional to each other. So if we increase the bandwidth to 2, this would go to 12 bits per second at a signal-to-noise ratio of 70. There is another way to look at this chart. Recalling Hartley's Law, C is equal to 2 by the bandwidth log base 2 of n, where n is the number of levels. As an example, consider this line right here representing 8 levels. You'll notice that it doesn't care what the signal-to-noise ratio is. All the way from 70 to 400, it's always the same. However, the signal-to-noise ratio must be greater than approximately 70. Or another way of saying that is you can have 8 levels provided the signal-to-noise ratio is greater than 70. Let's go ahead and work a few examples to make some more sense of this. Assume signal-to-noise ratio is equal to 1,000 and the bandwidth is equal to 500 hertz. Now be careful, the Shannon-Hartley limit needs absolute signal-to-noise ratio. Since there are no dB terms associated with this, we know that it is in absolute terms. Had the signal-to-noise ratio been in dB, we would have said SNR is equal to 30 dB, where that is calculated as 10 log of 1,000. The first step is to find the channel capacity. C is equal to B log base 2 of 1 plus the signal-to-noise ratio. C is equal to bandwidth 500 by log base 2 of 1 plus the signal-to-noise ratio. Gives us a channel capacity of approximately 5,000 bits per second. By the by, you have to be very careful in this section of the class because we have log base 2 and we have log base 10 that exist in the same problems. So watch out for that. Anyway, now that we know the capacity, we can find the required number of levels. Capacity is equal to 2 bandwidth log base 2 of n. So 5,000 is equal to 2 by our bandwidth log base 2 of n. That works out to 5 is equal to log base 2 of n. Breaking n out of jail, that's 2 raised to the 5th power, is equal to 2 log base 2 of n, which yields an n equal to 32. So a 32 level system with a bandwidth of 500 hertz with a linear or absolute signal-to-noise ratio of 1,000 will allow us to transmit 5,000 bits per second. Here's another example. You're asked to find the channel capacity given a 1 megahertz bandwidth and a signal-to-noise ratio of 20 dB. The Shannon-Hartley limit tells us that the capacity is equal to B log base 2 of 1 plus the signal-to-noise ratio. But be careful, be careful, be careful, be careful, because that signal-to-noise ratio is linear or absolute. It is decidedly not in dB. Yet your problem tells you that the signal-to-noise ratio is in dB. To fix that, 20 is equal to 10 log of signal-to-noise ratio. 2 is equal to log of the signal-to-noise ratio. We want to break this out of jail. It's 10 raised to the second power is equal to 10 log, of course that's base 10, of the signal-to-noise ratio, which gives us a signal-to-noise ratio equal to 10 squared, or simply 100. By the way, if you're getting lost at this point, go back and look at those videos about the Sneetches and the star on and the star off machine. You'll remember that 10 raised to the log base 10 of x is equal to x. Anyway, where were we? We had this equation. It required a linear signal-to-noise ratio. We converted 20 dB to 100. We can now use the equation. C is equal to our bandwidth, which is 1 megahertz, log base 2 of 1 plus 100, which yields a channel capacity of 6.7 million bits per second, or if you care, that's approximately 830 bytes per second, with the understanding there are 8 bits in a byte. As for the levels, 6.7 times 10 to the 6th is equal to 2 by 1 times 10 to the 6th log base 2 of n. 3.35 is equal to log 2 of n. Solving for n, that's 2 raised to the 3.35, which is approximately 10. In the real world, we're unlikely to use 10 levels. Instead, we can lower the performance and allow 8 levels, or we can increase the bandwidth and accept 16 levels. All right, that takes care of Hartley's Law, which tells us the channel capacity is 2 by the bandwidth log base 2 of the number of levels, and the Shannon-Hartley limit, which tells us the channel capacity is equal to B log base 2 of 1 plus the signal-to-noise ratio. It's the Shannon-Hartley limit with its recognition of the signal-to-noise ratio that ultimately determines the speed at which we can send information. As we close this discussion, I think it's important that we recognize that things can and will go wrong. There will be bit errors, which moves us into a new field of error detection and error correction. Here's a new concept for you. It's known as the bit error rate, which could be described as the average number of errors in a large block. For example, calculate the number of errors in a 5 megabyte file when the bit error rate is 1 in 100,000. That's 1 error for 100,000 bits. Using dimensional analysis, we start with the size of the file, in this case 5 megabytes. Sorry if I said that wrong before, that's 5 megabytes, where there are 8 bits per byte. And we said that there was 1 error for every 100,000 bits. Bytes and bits leaving errors. So there are approximately 400 errors. Depending on the nature of this file, that may be acceptable, but it probably isn't. So what we need is a way of detecting those errors and, if possible, correcting those errors. A primitive way to detect the errors is known as the parity bit. There are two types of parity. There's even parity and odd parity. Let's look at even first. Suppose you had this 8-bit sequence. To that 8-bit sequence, we will append a parity bit. You could think of this as a form of redundancy. Instead of transferring 8 bits, we're going to transfer 9, with the understanding that in even parity, the number of ones is even. So given this, you'll see there are 3 ones already, so the parity bit will be 1. In another example, if we had the sequence 1101, 0010, we would tack on a parity bit of 0, because there are 1, 2, 3, 4 ones already, which is even. So the parity bit in even parity will be 0. There's also odd parity, where the number of ones is odd. An example of odd parity, given the sequence 10110001, we would add 1 as the parity bit. So there are now 1, 2, 3, 4, 5 ones, which is odd. Or if we had the character 11010101, we would count the ones. So that's 1, 2, 3, 4, 5. So it's odd already. The parity bit would be 0. Now the idea behind this is that every once in a while, noise will take out one of the bits. For example, if there was a noise spike right here. Now when the receiver looks at this, it will count the ones. It will go 1, 2, 3, and it will say, no, there is an error. With this simple system, the receiver doesn't know where the error is, but it does know that there is an error, and sometimes that's good enough. You'll be glad to know that there are more sophisticated methods, one of which is the Reed-Solomon code. In this system, a block of data is sent. To that block, a Reed-Solomon code is appended. This Reed-Solomon algorithm is both error correction and detection. It can detect and repair a few bit errors in the data, or even bit errors that occur in the Reed-Solomon appended code itself. This additional information, this error correction code, is very important to us because it allows us to recover data even when it's damaged. For example, the scratch on a compact disc.